Let's watch how the direction of a stream of water can be changed by a comb. We'll start with this person combing a plastic comb through her hair. That's significant. That's important that she's combing it through her hair. What do you think can be happening while she runs the comb through her hair? And would it work if she used a metal comb or a wooden comb? When she brings the comb close to the stream of water, the water changes direction. It bends toward the comb. Before the comb is moved toward the water is all falling straight down. When the water is near the comb, it bends toward the water. Okay, so let's say you do the same experiment. You keep the comb in one position. So the water is bending toward the comb as it is in the drawing. Okay, the water bends toward the comb. What could you do to straighten out the bent stream of water as it flows past the comb? Well, let's think about this. Okay, we're talking about forces. And when we're talking about forces and how forces interact with each other, we want to draw a free body diagram to show how the forces are interacting. So what would a free body diagram look like for a particle of water in this stream? Well, here's a particle of water. It is being affected by gravity. So gravity is pulling it down. Then there's the force. The comb is clearly applying a force because the water is bending toward the comb. It's accelerating toward the comb. So we'll call this force of E, electrostatic force. So the water, as it moves past the comb, is actually being accelerated not straight down, not straight to the side. It's being accelerated. Remember, we have to add these vectors together. We need to find the resultant vector. So if we use the parallelogram method to find the resultant vector, we find that the water is being accelerated in this sort of diagonal direction. Now, if we want it to straighten out, we have to get it so that the only force acting on it is gravity, or the only force not acting on it, but the only force accelerating it is gravity. So that means that we want to have a net vertical force, but we want to have no net horizontal force. So that means we would have to have a force acting in the opposite direction of the same magnitude. And now the horizontal forces cancel each other out. And what you could use what could you use to provide this force? You could use another comb. You could use I don't know, a balloon. Remember, you can charge a balloon, but you would have to provide something that would be able to provide some kind of field force acting from the opposite direction. So if you run a couple of combs through your hair, put one on each side of the stream of water, then it should straighten out the water. Let's not forget this, because we haven't drawn free body diagrams recently, but let's not forget that when you are trying to analyze how forces affect matter, you want to draw a free body diagram to show how the forces interact. Charge and electric fields can attract or repel objects. Think about it. Why does the comb attract water? Why doesn't it repel? Would a charged comb have the same effect on other liquids? What questions do you have? Think about what other questions you can generate as we work through this lesson. Let's look at the images of lightning and other phenomena, and then write a list of questions. Pause the video, write a list of questions that you have about these phenomena in your notes. If you wish, you can include questions you might have about other electrostatic phenomena. So lightning is an electrostatic phenomenon. Why is that bee on the flower shown here? Well, when a bee lands on a flower, the pollen sticks to the bee by electrostatic force. So the bee can carry the pollen to another flower, and this is why honeybees or bees in general are so important to agriculture, because they carry pollen from one plant to another, so that plants can fertilize each other instead of just fertilizing within a very localized population. Here we see a comb, like the comb that attracted the water. Here we see a comb attracting little bits of paper. So combs can attract water. They can attract little bits of paper. What else do you think combs might be able to attract if you run them through your hair, or balloons, or other objects for that matter? Sometimes if you rub your feet on the carpet, you rub your socks on the carpet and then touch a doorknob, you'll get a little shock like this. What is this? Is this the same as what we saw in the first image? Is this the same as lightning? How are they similar? How are they different? When you put your hands on a Van de Graaff generator, remember the Van de Graaff generator builds up electric charge, static electric charge. And why does a person's hair stand up on end like this? What are the forces that are taking place that make her hair stand up? Think about it. Why would hair stand up like that? Lastly, what we see here is some workers grounding an electric system. So the electric system in your home, or in the building we're in now, it needs to be grounded, and so it's a safety measure. So this wire carries electric current into the earth. Okay, what questions do you have about that? What's the point of that? Think about how you could organize the different types of phenomena we just saw, and 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 that you mentioned in your questions. Think about how you could categorize those. How could you put similar or related phenomena together? Could you put them in some kind of order? Would you order them by the perceived strength? How would you determine the strength of the forces? How do you even determine force on some of those, like a spark or lightning? Would you organize them by the size of the objects involved, or by the distance from which the forces appear to act? We're going to look at a paragraph now, and this is from your Explore Explain, and on page 141 in your textbook. An electric spark from a doorknob is most similar to lightning. Both occur after charge builds up. Okay, if you rub your socks on the carpet, charge is building up in your body. Lightning occurs because charge builds up in the atmosphere, in the clouds. A ground wire, such as the wire attached to a lightning rod, that was the last image we saw, a ground wire, such as the wire attached to a lightning rod, provides a path that can prevent such a buildup. Signs at gas stations tell motorists to place gasoline storage containers on the ground rather than in the car or truck, and to keep the dispenser nozzle in contact with the container being filled. These precautions prevent a phenomenon most like a ground wire, which helps avoid a spark. As you can imagine, a spark at a gas station or at a gas pump could be disastrous. So we take every precaution we can to ground everything around us when we're at a gas station. Built up charge can flow through air suddenly as a small spark or a large bolt of lightning. A ground wire or a connection of dispenser nozzle to container to ground provides a path for charge to flow without moving through air, causing a spark and possibly starting a fire or explosion. Here we see 3 charged spheres hanging from insulated strings. So the charge cannot travel through the string. That's what insulated means. It means that electrons do not flow through that material very easily. A positively charged cube is brought near the center sphere. Use the positions of the spheres to determine whether each sphere is positive or negative? Well, this middle sphere, B, we see it moving away from the positive sphere, or away from the positive cube, I'm sorry. So if it moves away, then that tells us that it is also a positive charge because like charges repel. Now, A is attracted to B. A is moving toward B. So A has a negative charge because opposite charges attract. D is moving toward the blue cube, the positive cube. So D also has a negative charge because opposite charges attract. We're going to look at another paragraph that's also on page 41. The plus sign on the cube means that it has a positive charge. The sphere on the right is attracted by the cube. It must have the opposite charge as the cube because opposite charges attract. The opposite is true for the center sphere. The sphere on the left is attracted by the middle sphere and the cube. You determine that the spheres on both ends have a negative charge because they're attracted to the positively charged cube. The center sphere must have the same charge as the cube and the same effect on the end spheres. When you model the charge on your hand and a doorknob, you might use positive and negative symbols to show the patterns of charge. You treat positive and negative charge equally. Okay, so negative is not less than positive. Positive and negative are just names given to show the different types of charges, and they were named by Benjamin Franklin hundreds of years ago. And they do add together, like a positive and a negative charge will add up to zero, but a negative charge is not less than a positive charge in any way. An atom is made up of a nucleus, an electron cloud. The electrons are, you can't pinpoint the location of an electron around a nucleus, but the electrons move around the nucleus so fast and they're so small that we represent them by an electron cloud. The electrons were actually the first subatomic particle discovered, and then the nucleus. And the nucleus is made up of protons, which are positively charged, and neutrons, which have no net charge. The neutrons help hold the nucleus together. So if you're wondering, wait a minute, how do you cram all those protons together? Don't they repel? Yes, they do repel. But there's another force other than the electrostatic force that holds the nucleus together. And that force is strengthened by the presence of neutrons in a nucleus. Electrons and protons are particles of matter, though tiny, especially electrons. Electrons are ridiculously small, much smaller than protons. During interactions, they are conserved. Because charge comes from electrons and protons, charge is also conserved. Equal amounts of positive and negative charge appear when electrons and protons are separated. So the total charge remains the same. For example, walking across a wool carpet moves electrons from the carpet to your body. So your body gets a negative charge. Electrons move to your body gets a negative charge. The negative charge on your body matches the opposite charge on the carpet. So as your body gets a negative charge, the carpet gets a positive charge. The carpet's electrons are going to your body. So your body's negative, the carpet's positive because your body now has more electrons than protons, and the carpet now has more protons than electrons. So the net charge on your body and the carpet together, if you look at your body and the carpet together as a system, the net charge, the total net charge is unchanged. The particles of matter that make up atoms are conserved along with the charge on them. When charged particles are separated, such as when a negatively charged electron is removed from an atom, equal amounts of positive and negative charge appear, but the total amount of charge remains constant. Polarization occurs when there is shifting or alignment of positive and negative charges within a neutral object, typically an insulator. So the plastic comb is an insulator. What happens? Well, the positive and negative charges shift within the comb and the pieces of paper, and so they attract each other. It's a little easier to see with water. Okay, well, with the comb, uh, actually, the comb when the girl ran the comb through her hair, she was adding electrons to the comb. So she was taking electrons from her hair, transferring them to the comb, so the comb got a negative charge. Now, when you bring the negatively charged comb close to the pieces of paper, the negative charges in the comb repel the negative charges in the paper, so the paper becomes polarized. You see the negative charge gets pushed to the opposite side of the paper, and that leaves more positive charge on the near side of the paper. The paper becomes polarized, so the paper has a negative end and a positive end. And since the comb has a negative charge and the paper has a positive end, the negative charge on the comb is attracted to the positive charge, the positive end of the paper. So the paper doesn't actually need to be charged to be attracted to the comb. We see the same thing in water. Water has a negative end. The oxygen end of the water is negative, and then the hydrogen end of the water is positive. So the oxygen atom has a partial negative charge, and the hydrogen atoms have partial positive charges. The hydrogen atoms attract oxygen atoms in nearby water molecules. So this negative end is attracted to this positive end of this water molecule and this positive end. So the hydrogen atoms attract oxygen atoms, but repel other hydrogen atoms. So water molecules align themselves in this way. This is similar to the way the comb interacts with the polarized bits of paper. In still water, or as water freezes, the molecules could align in a structure. If you have ever done a belly flop into a swimming pool, you have experienced the way that water molecules stick together. And this is called cohesion. Okay. If you've even just gotten wet in a swimming pool and gotten out, you've noticed that the water sticks to your body. That's called adhesion. And this is due to the polarity of the water molecule. Polarity means that there's a positive end and a negative end. Not all molecules are polar. Water is quite polar. Some molecules have no positive end or negative end. Okay, lastly, we're going to talk briefly about electrostatic induction. Electrostatic induction is a way to charge an object. The properties of insulators, like these styrofoam cups, and conductors, like these pie pans, can be used to build up a large amount of charge on a conductor. When a highly charged insulator is brought near a conductor, a large separation of charge is produced in the conductor. If you wanted to keep this aluminum pan charged, what would you do next? Well, what you would do is remove the grounding touch, because you want to remove the pathway by which electrons are leaving the aluminum pan. You want to take it away from the ground. And if you take it away from the ground, then the pan will remain charged, because the electrons don't have a pathway out of the charged object.